All right, let's dive into a really cool and classic coding problem, finding the leaders in an array. This is a fantastic example of how just a small shift in how you look at a problem can lead to a way more efficient solution.
So, first things first, what in the world is a leader? Well, the definition is actually pretty simple. An element is a leader if it's strictly bigger than every single element to its right. Oh, and there's one little rule. The element at the very end of the array, it's always a leader, kind of by default, because, well, there's nothing to its right to compare it to.
Okay, let's make this real with an example. Say you have the array 1, 2, 5, 3, 1, 2. The leaders here are 5, 3, and 2. So why? Well, let's break it down. 2 is the rightmost element, so it gets a free pass. It's a leader. 3 is a leader because it's bigger than the 1 and the 2 to its right. And 5, of course, is bigger than everything after it. See how that works? Pretty straightforward, right?
Now, how would you actually go about coding a solution for this? The first thing that probably pops into your head is the most direct way, what we often call the brute force method.
The logic here is pretty simple. You pick an element, and then you loop through every single element to the right of it. If you find even one number that's bigger, boom, it's disqualified. It's not a leader. And you have to do this for every single element in the array, which means you've got a loop running inside another loop.
And that of loop, yeah, that comes with a pretty big performance cost. In computer science, we call this O of n squared time complexity. What that really means is, as your array gets bigger, the time it takes to solve the problem gets way bigger, like exponentially. It'll work fine for a tiny array, but it becomes painfully slow for anything large. So you're probably thinking, okay, there's no way this is the best solution. For a problem like this, there has to be a smarter, more clever way to do it. And you would be absolutely right. And that brings us to the SMART approach. This is where we flip the whole problem on its head and find a much more elegant way to solve it.
So what's the big secret? It's this one simple idea. Instead of starting from the left and looking to your right over and over again, what if we start from the right end of the array and move left? I know it sounds simple, but this one change is the entire key to solving this thing efficiently. So why is this so much better? It comes down to two things. First, we get a freebie. We already know the rightmost element is a leader, so that's our starting point. And second, as we move to the left, we only have to remember one single number, the biggest number we've seen so far on the right. If the number we're currently looking at is bigger than that max, well, it has to be a leader.
Okay, enough talk, right? Let's actually walk through an example step by step. Seeing this thing in action is gonna make it all click. Here's the array we're gonna use: 16, 17, 4, 3, 5, and 2. We're starting with a clean slate, an empty list for our leaders, and no current max just yet.
All right, step 1. We start at the very far right with the number 2. Remember our rule? The rightmost element is always a leader. So we add it to our list, and we set our current max to 2. Easy enough.
Now we take one step to the left. We're looking at the number 5. So we ask the question, is 5 greater than our current max of 2? Yep, it sure is. So 5 is a leader, we add it to our list, and this is the crucial part, we update our current max. The new max is now 5. Let's keep it rolling. Move left again to the number 3. Is 3 greater than our max, which is 5? Nope, not at all. So we do nothing. 3 is not a leader, and we just move on. See how we didn't have to scan anything? So clean. Next up is 4. Same question. Is 4 bigger than our max of 5? Again, nope. So 4 is not a leader. We just keep heading left. Okay, now we land on 17. Is 17 bigger than our current max of 5? Oh yeah, absolutely. So you know what that means. 17 is a leader. We add it to our list, and we have a new champion. Our max is now 17. And finally, we're at the very first element, 16. Is 16 greater than our max of 17? Not even close, so we just ignore it. And just like that, we've reached the beginning of the array. We're done! So, what are we left with? Our list of leaders is 2, 5, 17. But wait, that's backwards from what we expect, right? That's just because we built it from right to left. So the very last step is to just flip the list around, and we get our final, correct answer, 17, 5, 2. So let's just step back for a second. Why do we even bother with this new approach? The final analysis really shows just how powerful this simple change of perspective really is. Let's put them side by side.
The brute force method was O of n squared. Our new optimal method, it's just O of n because we only had to pass through the array one single time. This is a massive, massive improvement. For a huge array, we're talking about the difference between something taking hours and something taking a split second. It's a total game changer.
So what's the big takeaway here? This isn't just some clever trick for one single problem. No, this is a fundamental problem-solving pattern. From now on, whenever you see a problem where an element's condition depends on the stuff to its right, a little light bulb should go off in your head. You should immediately think, hey, what happens if I try solving this from right to left? Trust me, asking that question can unlock elegant solutions to all sorts of other problems.